I'll just introduce.
Sure. It's working.
Hello, welcome back to our second lecture. So we have our second lecture on lattice QCD at non-zero temperature density by Dr. Petreczky. And most of you know about his works, so I don't need to introduce him to you. And he's among many exciting works he's doing on lattice. One of his major expertise is on heavy quarks, and he will tell us more about this in his first lecture.
Oh,
So
thank
Peter,
you very
please.
much for introduction. So I decided to give kind of overview lecture on QCD at non-zero temperature with emphasis on heavy quarks, but of course the topics I will cover go beyond heavy quarks, so some of them closely related. So my general idea is to give you some idea what is a deconfinement transition in QCD and how color screening works. Then we'll discuss the chiral transition at non-zero temperature and density, maybe just briefly, or maybe not so briefly, but at least define what it is and how it is related to the deconfinement transition. I will give a brief overview of equation of state at non-zero at zero density, so just finite temperature but zero baryon density. And then I will go to discuss the Taylor expansion of the QCD pressure, because that's something that gives you kind of introduces the concept of fluctuation and correlation of conserved charges, and that's directly relevant for the charm degrees of freedom, so one of the heavy quark degrees of freedom across the chiral transition. And then finally go to the QCD bound states, so bound states of heavy quarks, heavy quark diffusion coefficient from lattice QCD, and the concept of complex potential at non-zero temperature and density. So through the talk, so there's a lattice talk, I will certainly make contact whenever possible, comparison whenever possible with weak coupling calculations. So I will be discussing a little bit the comparison of lattice QCD results, the so-called Hall-Sherma loop perturbation theory, electrostatic QCD, or the potential non-relativistic QCD. So all these kind of different ways to do the weak coupling calculations and finite temperature QCD. And on the other side, kind of in the lower temperature phase, I will do the comparison with hadron resonance gas model. I will introduce this concept and also how one should think about it, how it emerges from when you do try to do thermodynamics in terms of hadron degrees of freedom. So it's a lot to cover. So let me start. So just to give you a basic idea of why do we think there will be a transition from hadron matter, hadron gas, to some other new states of matter. And actually, this idea is very old, predates QCD by decades. And it was first put forward by Pomeranchuk. And his idea was that, well, the only thing they knew about back then about protons and neutrons, that they have a finite size and not point-like objects. And the concept was that if they're not point-like concepts, somehow this idea that you could do a hadron gas or even imagine a hadron gas doesn't make sense beyond some temperature. And that's because if you go to very high temperature, you have a relativistic system, you create more and more hadrons, more and more protons, neutrons, pions, whatever. And at some point, all these states start to overlap. So somehow the thermal wavelengths will be much shorter than the size of the object, and certainly then the object itself cannot exist. And so that's what I try to picture here. So you start with hadron gas. In more modern terms, you would think of this as being composed of quarks, right? And then you increase the temperature, the density of these hadrons increases, they start to overlap. And at that point, of course, the idea that a quark, specific quark belongs to one hadron is kind of start to be less and less meaningful, right? Because a hadron backs overlap. And if you push to extremes, then of course there is no kind of hadrons anymore, right? Because the quarks and gluons is sort of delocalized because they're not bound to any hadrons. And now, so that's how we think about deconfinement. So increase the temperature density, you go from hadron gas, where quarks and gluons are confined inside of hadrons. Hadrons start to overlap, and then at very high temperature, you form Quark-Gluon Plasma. Why it's Quark-Gluon Plasma? That's because the distance now between quarks and gluons now becomes very short, so it's order of the inverse temperature, and that gives you the typical scale of interaction. And you know that the coupling constant in QCD, alpha s, is much smaller when you're talking about interaction at small scales. So therefore, it's kind of a weak coupling regime. Now, with a weak coupling regime, the non-perturbative feature of QCD will be washed out, so it will be chiral symmetry will be restored. And of course, you have enough color charges, so eventually, as in usual plasmas, they will get screened. So this new state of matter will have something like a color screening instead of confinement. So Quark-Gluon plasma is a deconfined chiral symmetric matter with color screening. Now, when we think about Quark-Gluon plasma, so we think about this function of the, or in general, a strongly interacting matter, as functions of temperature and baryon, let's say baryon density, mu, or given by, governed by chemical potential, mu. And what we know is that this transition from between kind of hadron gas to Quark-Gluon plasma is a crossover at zero density and also at moderate baryon density. Eventually, there is a conjecture that this crossover ends in a critical point, and then from there on, it's a first order phase transition. So that, of course, we don't know yet from the lattice, but that's how we think about it. So now, so I mentioned already chiral symmetry, so let me just discuss briefly what it is and why it's important. So, so the QCD Lagrangian has a symmetry in the limit when the quark masses can be ignored. So we know that up and down quark masses are much smaller than the typical scale of QCD. That's the scale when the QCD interaction becomes large. And the QCD Lagrangian is invariant on the flavored chiral rotation of the fields. So it means that you could, if you decompose the quark fields to left moving and right moving components, you could rotate them independently. You could do this. So that's basically the chiral rotation. Now, if you calculate something which is called the chiral condensate, which I will talk about psi bar psi, expectation of psi bar pi in QCD vacuum, you could also write it as this kind of expectation of this quark linear. And it's clear that when you this condensate is non-zero, the chiral condensate is non-zero, then the symmetry where you could rotate independently left and right in the massless limit is broken. So although it's a symmetry of the Lagrangian, but it's not realized in nature or in the spectrum, that's kind of what we know is the Nambu-Goldstone realization of the symmetry. And that has profound consequences in QCD, namely that QCD in the low energy limit, if you describe by hadrons, it's in some sense weakly coupled, right? So hadrons at very low energy interact weakly, relatively speaking, right? So you could use something like chiral perturbation theory, so you could actually understand the interaction with hadrons. And of course, the other thing is that hadrons with opposite parity, because this chiral symmetry will have very different masses. If they were, if the chiral symmetry wouldn't be broken, then of course, state with opposite parity would be degenerate, but that's certainly not the case as we see it from QCD. So just remember that chiral symmetry breaking is to some extent is a reason why hadron gas in some sense is weakly interacting at very low temperature. Now there is another symmetry, so you could ask, okay, we're talking about flavor symmetry, flavor chiral rotation. You could also do, obviously, naively at classical level, you could also rotate without flavors, a single flavor singlet chiral rotation. And that's, as a classical level, is a symmetry of QCD, but is broken by the anomaly. And that's the reason why the eta prime is so heavy and the pion and the A0 fields are not degenerate. And they, in fact, have very different masses. Now, if you go to high temperature, we expect that the chiral symmetry will be restored, as already mentioned. And also, to some extent, so the chiral symmetry is restored, so the psi bar psi will go to zero, as I mentioned. But then, of course, what happens to U1 symmetry is not so clear. It's anomalous, so it's not really restored at any temperature. So the effect of breaking of UA1 symmetry anomalous, so the effect of anomaly at high temperature is much smaller. So when we think about kind of phase diagram in theory space, right? We have the quark masses, and already talked about in the massless limits, you have chiral symmetry. So that's what governs this transition line or even the crossover line. And there is, of course, other limit where you could imagine the quark masses are very large, so we can go to infinity. And then what happens, then, of course, we have the deconfinement transition I will explain later on. But overall, the phase diagram of QCD can be sort of what is known as Columbia plot. So you plot the nature of the transition in QCD as a function of quark masses. So we have this two light quark masses up and down. We have the strange quark mass, which is not that light, but it's also not heavy. So it's relatively light degree of freedom. So those will govern the behavior of this transition. So if you go to the limit when the strange quark mass is very small and the up and down quark mass is very small, then you have a chiral transition, and that at very small quark masses is believed to be a first order transition. Yeah.
So what is the status now? Some people are arguing that this first order region missing this.
Okay, I mean, I won't talk about it, but the quick answer to the question is nobody did a calculation with controlled uncertainties, right? So if you do staggered calculation, effectively always in the world of heavy pion mass, and the state, of course, if your pion mass is not here because you didn't take the continuum limit, but somewhere here, of course, no question, you could put the quark masses down to 0, and some of the pions will be heavy, and there is no surprise that you don't see it. Nobody did calculation with, let's say, chiral fermions down to that small quark mass. If that would be the case, then I would believe, but based on staggered, you cannot make this statement. Okay, so now if you go to the opposite limit, then all the three quark masses are very large, so kind of almost going to infinity. Of course, in this corner, you have a first order transition, the confinement transition, which I will discuss later. Of course, any first order transition doesn't just disappear when you turn on some disturbing fields, like magnetic fields. It remains first order, and this first order region, the confinement transition, survives up to, let's say, almost to something like the charm quark mass. So it's for very heavy. If in QCD we only had heavy quarks, you would only have a first order transition. And here we have another symmetry, which is not the symmetry of QCD Lagrangian, but it's a symmetry of QCD partition function at finite temperature. And that the center symmetry, Zn center symmetry. The Zn is a subgroup of SUN, if you think about not just QCD, but in general, SUC gauge theory. And this breaking of this symmetry is associated with the confinement. Now, the chiral symmetry already mentioned. So here we have a first order transition. Now, of course, we think that the physical point is somewhere here because after all, the strange quark mass is much larger than the up and down. It's still smaller than QCD, but it's kind of somewhere, if you want to put in this case, somewhere here. So the physical point is in the crossover region, far away from this first order transition, which, by the way, I mean, if you estimate, there is no direct calculation. Some old estimates, they say, well, 67, 50 MeV. Also, effective models suggest something a very low order. So if you want to do an estimate, which is, let's say, a model-based estimate, some linear sigma model, you would end up with a 50 MeV here, or between 50 and 100, let's say. There are large uncertainties, but so getting there with lattice calculation is not easy, and certainly when you have finite lattice artifacts, it's almost impossible as of now.
The FRG people, they also gave the same numbers there, or?
Yeah, I would rather not comment on that. So now the question is, suppose you keep the strange quark mass fixed and imagine how the transition would go if you lower the up and down quark masses. In principle, the conjecture is, or our understanding is, that it could be a second order transition. Why second order transition? And that has to do with the fact that if you restore the axial symmetry and the vector SU2 symmetries, the isospin symmetries, and the group is O4, so somehow the QCD transition is related to O4 spin models, and O4 spin models have the second order transition. So the idea is that if you go from physical point where the transition is crossover towards small and up and down quark masses, keeping strange quark masses at the physical value, then you will hit a second order transition. And that's how we think about chiral transition at the moment, as that it's kind of a remnant of a second order phase transition in the limit of up and down quark mass is going to 0. Okay, so now, so that's the general picture. So now let's come to the lattice. So what do we do on the lattice, right? So we want to study QCD at non-zero temperature. And when you study things at non-zero temperature, let's say you want to calculate an expectation value of some operator O, that means that you have to trace this operator with the corresponding statistical operator, so grand canonical statistical operator. And you interpret this operator as a Wolfson operator in imaginary time, just as for now you put mu to 0. So, right, you just have beta h, and beta will be your finite extent of your Euclidean time. So beta is 1 over temperature. And if you do that, right, then you could always write down the path integral representation of this trace in terms of path integral. So basically in terms of path integral over gluon fields and over the quark fields. And what you're ending up is the field theory of QCD in a finite box in a time direction. So the time is compact now, goes to 0 to beta. The beta is the inverse temperature here. And of course, the effect of the temperature is encoded in boundary conditions. So the gluon fields obey periodic boundary condition, quarks obey anti-periodic boundary condition. Now, this is an integral function, so that we can do on the computer. So what do we do? So we discretize our Euclidean spacetime. And when you discretize the Euclidean spacetime, then of course integral function becomes a usual integral with very large dimension, 1,000 million, depends on your lattice size, right? And then you could rewrite this as something maybe more manageable on computers. So here, of course, when you discretize, you do kind of a Wilsonian discretization. So you replace the gauge fields by the gauge connections, or a gauge connection between 2 points on the lattice. So that's a gauge length, mu, u mu, which is just exponential to the gauge field. You could integrate out the fermions explicitly because the QCD action is bilinear in the fermion field. So that gives you the fermion determinant. So you have to basically evaluate this integral over all the gauge fields on your lattice with the fermion determinant and the gauge action. And of course, for mu equals 0, you can do that via Monte Carlo method, given that it's a very large dimensional integral. So that's what I picture here on the lattice at finite temperature. You have a volume and sigma lattice sides. The time is compact, so 1 of the temperature is equal to the number of lattice sides time direction times the lattice spacing. And now you have to take the continuum limit, which means that lattice spacing go to 0, the temperature has to be fixed. That means that eventually also the temporal lattice extent should go to infinity, but such that the spatial number of spatial points and sigma over n tau should be fixed, right? So you want to remain in a finite box, a finite temperature box. So somehow this should be infinity, whereas that should be finite in physical units. So meaning that if you want to take the continuum limit, then you have to go to larger and larger number of time slices and tau. And of course, there is a cost for doing that, and numerical costs go like the lattice spacing to the -7th power, or the 7th power of the number of time slices. And of course, that's difficult to beat. So in some sense here, in order to do the calculation manageable, as you will see, we do calculation with n tau equal 8, 12. Sometimes we do it much larger when it comes to, for example, for doing heavy quark property, but n tau is not always very large, right? So in order to take this limit, n tau to infinity, you really need to rely on improved discretization schemes, so not the simplest discretization schemes like nearest neighbor. You have to go beyond that, and there are kind of different improved action. In the staggered case, go under name P4, A squared, that's stout. HISC stands for highly improved staggered quarks. So you could only do this calculation using highly improved action. And that's, by the way, tied to your question. When you do unimproved actions, and people still do, of course, you get all kind of weird results. It's very difficult, of course. You would think you take the continuum limit, and then it should be fine, but in practice, it doesn't work. It's even with the most powerful computers, you cannot get close to the continuum unless you do discretization effect. Now, if you have a chemical potential in the game, so you have a chemical potential, let's say, to baryon charge, then or quark, any quark number, then this determinant is complex, and then of course you cannot interpret this combination of exponential gauge action and the fermion determinant as kind of weight in Monte Carlo simulation. So that's the infamous sign problem, and these Monte Carlo techniques are not applicable. Now, if you want to do some thermodynamics at chemical potential, what you could do, you could expand your partition function, and then the expansion coefficient evaluated at mu equals 0, and that, of course, you could calculate. So that's one way to circumvent the sign problem in QCD, at least when the chemical potential is not too large. Okay, good. So now we have this lattice QCD setup, and I talk about deconfinement and transition and confinement, right? And how do we study this confinement transition? For some reason, the fonts are weird, but okay. Maybe I have to. Okay, now nothing I could do about now. Maybe in the next lecture, I will go through my slides and see what's going on. So you could study meson correlation function. So the idea is that you create a meson state. So meson is considered a quark and anti-quark, right? So on the lattice, you take this quark bilinear at point X and point Y. So you think about a meson as kind of being a non-local state, right? So not a point-like state. So it's X and Y, that's a location of quark and anti-quark, let's say. So you have corresponding with a quark annihilation operator, quark creation operator at point X and point Y. And to make this everything invariant, we introduce a gauge connection. So some sort of gauge ring connecting point X and point Y, and some gamma matrix to put a quantum number. So if you put gamma 5 here, that will be a pseudo-scalar meson, so the pion, or a sigma meson if gamma is 1. But you could create any combination number. So now you calculate this correlation function on the lattice, right? And the idea is that when you go to large time, large Euclidean time, now it's, you think about 0 temperature, then this correlation function is exponentially suppressed. So it could be written as sum of exponent. And the exponential, that's basically the masses of your mesons. And of course, you have the ground state mass, that's easy to extract. And of course, you have all tower of excitation. So that's a sum. So the higher excited state will be suppressed. So in the really infinite time limit, you dominate it by your ground state meson. So if it's a pseudo-scalar channel, so gamma 5, then you have your pion here, right? Now, you could also do the similar exercise for static quarks. So you could now consider, instead of going from considering pion, you could say the quark is very heavy. You go to infinitely heavy quark. In the limit of infinitely heavy quark, of course, the Dirac equation simplifies to this equation, right? So you just have only the gauge fields, A naught, the temporal gauge fields. And this equation you could formally solve like this, right? So you have this path integral, path ordered integral of the A naught fields across from 0 to tau. And that's basically the Wilson line, the temporal Wilson line of the gauge fields. And that's how you could relate then this operator, quark operator psi at point tau, at time tau to the initial point, or initial time 0, to this Wilson line. So when you insert this expression to this operator, and on the lattice, of course, it's easy to realize this operation, this operator, so the time ordered exponential of A naught field is just a product of gauge link in the time direction. So you use 0 from 0 to tau. So now you insert it, right? And you calculate the correlation function of heavy quarks. Then you could integrate out the heavy quark degrees of freedom at the end. You integrate them out because it's a path integral. Right? And what all remains from this operator is basically the Wilson line L in the time direction. And the gauge link that connecting points X and Y. And similarly for the, so that's kind of for the, you have operator, creation operator for meson J at time 0 and annihilation operator J at tau t, at time tau. And of course, then where you have this this one combination, and that's the creation operator, right? And then when you look at it, right, and you trace it over to get rid of all the color indexes, then that's basically what ending up is what you know as a Wilson loop, right? So you loop around the lattice, so there is x and y here, and 0 to tau here, 0 to time, 0 to beta, I should say. It's t here is not the temperature, but the time extent, which is which I denoted here, t. But in any case, so now you could do the similar decomposition, spectral decomposition from the Wilson loops. So you have energies now of a static quarks and anti-quarks, separated distance r. So that's r is the distance between x and y, and exponential decay. And of course, if you go to infinite time, you're only isolating the ground state. And the ground state, so the lowest energy state of a static quark and anti-quark is what we know is the static quark anti-quark potential. And the confinement now means that the energy of this quark anti-quark state grows as the distance r grows. So the separation between quark and anti-quark grows, and that grows linearly, and the coefficient of this linear behavior is the string tension sigma. Of course, at short distances, you have a usual Coulomb interaction. The coupling is small, then you could do perturbations here, and of course, you get the Coulomb as well. So somehow you could think about the potential as a combination of one gluon exchange at short distances plus this non-perturbative string tension. So when you go to large distances and also large tau, there's this linear rise of potential. Also applies as the Wilson loops obey the area law. That is, the Wilson loop is an exponent of sigma r times tau. So that's basically as exponential decay of this Wilson loops as you increase both r and tau is the area of this Wilson loop. So that's the area law, and that means confinement. So confinement, at least in pure glue theory, so then you don't have any quarks, just have SU3 gauge theory. That's basically the area of Wilson loops. Now, we talked about the ground state of this kind of static Mason correlation function. But of course, there are, in principle, the other terms contributing to that, so N2 and larger. And those, of course, also describe a combination, also describe an energy of a static quark pairs, the excited energy. So if you think about the energy of a static quark and anti-quark as a string, of course, you could imagine that the excitation of the strings, and of course, that's how actually string theory emerged. I mean, they thought that hadrons, all the hadrons are basically strings, and the excitation spectra of hadrons are excited state mesons, baryons are kind of string excitations. So here are some lattice results, just you could tell from the color, some of them are old. So the first two lattice results were done, lattice calculation were done in zero flavor, so no quarks, just pure SU3 gauge theory. And you see very nicely that the distances of order even smaller than a Fermi, you see this linear rise of the potential. I always plot here everything in units of R0, and that's basically how you set the scale in that, or one way to set the scale in lattice calculation. It will appear in the next slide. So you could, if you have a potential, you could calculate the derivative of the potential, and then you could require that this derivative times r squared gives you this number, and this number was arbitrarily chosen with some physics consideration to be 1.65. And when you do the lattice calculation, you estimate it, then it gives you the value of this dimension of full scale, R0 to be like something like 4-to-1 Fermi. You could also estimate the string tension. That's how also in the early days one estimated the lattice spacing using the string tension. But if you estimate the string tension using some physical input like a meson decay constant or baryon mass, then you get the string tension to be 470 MeV. So that's a calculation of the ground state potential from long time ago, as you could see from the quality of this figure. also the calculation of the excited state potential, the hybrid potential, the threshold here. So the black line is the ground state potential. And then, of course, you have a tower of excitation. And the quantum numbers here are just the quantum numbers of let's say, of what you use to describe diatomic molecules. So you don't need to go into detail, but just to tell you that these excited potentials as well, or hybrid potentials. And of course, we nowadays do calculation also in full QCD. And here I show now the potential in full QCD for different beta values. So beta here is a gauge coupling of the lattice. Is basically its inverse of the usual gauge coupling times some color factor, 2nc or something like that. Okay, good.
These hybrid potentials, people have introduced these gluons, right? So
yeah, I mean, if you want to understand them, you could think about as some quark and anti-quark and some gluonic fields in between them, in addition to the string.
But then the potential can become gauge dependent in that sense.
A gauge?
Dependent.
Not really. I mean, the hybrid potential gauge invariant. So when you think about it, you input some electric field on your Wilson. So formally, how they defined or how you calculate them, you put electrical magnetic fields on the Wilson line. So it's just insertion of electrical and electromagnetic fields, and you still have a closed loop. You always have a closed loop, so that's gauge invariant. I mean, you could do it also from Wilson loops, right? You could extract this. So if you do a very accurate calculation of Wilson loops, you can extract the ground, not only the ground state, but also the next excited state you could get, at least the lowest one. And of course, getting the time spectrum is more difficult. But conceptually, you just do a Wilson loops and all of this potential in there. Okay, good. Okay, so here I guess kind of explain more a little bit. So it was kind of jump a little bit ahead just to give you a sense of how where the lattice some history of the lattice calculation and where we stand. Now I want to go back to the center symmetry and deconfinement transition. So the concept is already ZN symmetry breaking. So ZN is a subgroup of SUN gauge theory. And we know that the quarks transform non-trivially under ZN, obviously. And what it means, I mean, the breaking of the symmetry means that static charges in fundamental representation in a pure gluonic theory are kind of screened by gluons. So it's kind of a bizarre. So you imagine a pure gluonic plasma, you put a static quark in there, and its color charge gets screened by gluons, although not by quark, but by gluons. So that's what it means. So it's, when you think about it, it's a kind of bizarre. So what do we mean by here? So we have already mentioned the Wilson line in temporal direction. So when you trace it, that's what's a Polyakov loop. It's called a Polyakov loop. And again, you have this standard gauge variable. The Polyakov loop, if you do it on the lattice, it is a product of this gauge link along the time direction. You trace it, and you when it's you don't have to, but it's conventional to normalize the number of colors. So as I also mentioned, that you have the lattice spacing. Now the lattice spacing in lattice QCD calculation is controlled by beta, the gauge coupling, which is in that case is defined as the usual gauge coupling G, but the inverse of it. So it's 2nc over G squared typical, or sometimes a prefactor. If you use improved action, it could be some other prefactor instead of 2, but canonical is 2nc over G squared. So just keep in mind that when we do lattice calculation, we have to vary the temperature. We fix n tau, we vary beta. Beta is this combination 2nc over G squared. And then, of course, we have to take the continuum limit. And the way we take is the continuum limit set n tau to infinity by keeping this ratio and sigma, the spatial number of points to the temporal number of points, also going to infinity, at least being some large number, right? So that's how we take the continuum limit and thermodynamic limit. But at each fixed n tau and sigma, we vary the temperature by varying beta. Now, of course, the gauge links have this gauge transformation properties. And of course, the action is gauge invariant. So that means that if you do this rotation of your gauge fields, the action, QCD action is invariant. But there is a bigger symmetry when you're at finite temperature. If you look at the partition function, you could make a transformation of the gauge fields that's not just periodic, right? So now we have to obey the periodic boundary condition. So normally you would say this gauge transformation matrix omega should be periodic. But if you consider pure gauge theory, the partition function of SU3 gauge theory, for example, SUN gauge theory, then there is a larger class of gauge transformations that is allowed. It's namely where this gauge transformation is periodic in time up to a factor C, which is an element of the N symmetry, of the N group, the subgroup of SU3. So there is a large symmetry of the partition function, which is not in the QCD Lagrangian, but the partition function has this symmetry of pure gauge theory. Now, if you consider this Wilson line, the traced Wilson line, the Polyakov loop, in the time direction, obviously that transformed non-trivially on this Zn rotation, this C factor, right? So if you have this gauge transformation, which has this extra center element, then it transforms like this. So if the Polyakov loop is 0, then of course you have this symmetry. If the Polyakov loop is 0, then this Zn symmetry is spontaneously broken. And one can show, and that was shown by Polyakov itself, but also by McLaren and Svetitsky, that the physical interpretation of this Polyakov loop expectation value is nothing but the free energy of an isolated static quark. So in that sense, if Polyakov loop becomes non-zero, that means that there is a deconfinement, and isolated, the free energy of an isolated static quark in a gluonic plasma is finite. And therefore L is also finite, so it's non-zero. So of course we could calculate that on the lattice, and I will show next slide how the calculation look like. One thing to keep in mind is that there is, of course, when you calculate any Wilson line operators, there is need for a normalization. If you leave it normalized, it has a self-energy divergence, right, from this oops. Self-energy divergence 1 over A, and of course that has to be removed before taking the continuum limit, so that's something to keep in mind. And here I show, again, some odd numerical results from lattice QCD calculation pure gauge theory for different lattice spacing. So recall that lattice spacing varied now by, the temperature is varied by varying beta. So here, for each n tau, we have a variation of the temperature, and continuum limit means that we have to go to larger n tau or mt here. Right, and what you see is that indeed the bare loop, so that's basically the numbers that come out from the lattice calculation, would go to 0 if you take the naive with a continuum limit. No, the scale 0.3, that's as you will see that the scale where you would expect it to be, kind of after normalization for n tau 4, it's close to that scale, but it's getting much smaller than you go to the continuum limit. Okay, but that's fine. You could work at finite lattice spacing if you just want to study the deconfinement transition, and that's what has been done over the years. So you at fixed finite lattice spacing, you don't worry that in the continuum limit, the quantity eventually goes to 0 and need to be renormalized, but renormalization is a UV property. So when you study phase transition with IR, then it doesn't matter. So you could just finite lattice spacing, you could calculate Polyakov loop, consider the order parameter and use it to study the deconfinement transition. And typically, if you have any phase transition, then you have you consider the order parameter, the fluctuation of the order parameter to locate the transition point. In other words, the Polyakov loop susceptibility, the fluctuation of the Polyakov loop, should have a peak at some well-defined temperature, or and the temperature, as I told you, is related to this gauge coupling beta, not to confuse with the inverse temperature. So you do the calculation at several several temperatures. So some of them are shown as error bars. You combine all this calculation using what is called the multi-histogram method. To calculate the susceptibility, you could really draw these nice bands, and you clearly see a peak at some beta C, which is gauge coupling corresponding to the critical temperature. Now, when you have this gauge coupling at beta C, you convert it to the lattice spacing, right? And that gives you the temperature in some units, R0. And now you have to take the continuum limit, so you have to set A to equal 0. And here I show, again, I show here basically the results of the deconfinement transition temperature TC units of R0, scale which I introduced before as a continuum limit for A. So here's A in TC units. And here different discretization effects. Again, you see the Wilsons, the most naive discretization effects. You see a sizable slope. You have improved discretization like Iwasaki. They have much smaller dependence on the lattice spacing. So that's why using improved discretization is important, especially when you have fermions in the game. So it's a continuum limit. Of course, what happens at all this different discretization, so the transition temperature itself, the phase transition temperature deconfinement depends on the lattice spacing and also depends on discretization. But when you go to the continuum limit, it goes to this universal value 0.75. Now, you could go further, and now we say, well, there is a transition, but there is no, strictly speaking, phase transition in a finite box. So how do we know what's the order of phase transition in thermodynamic limit? Well, you have to do finite size scaling. So here I show one volume, 32 cube, as this lattice spacing corresponding to 8 and tau equal 8. Now you have to go to larger lattice spacings, or larger volumes, and see how the height of this Polyakov susceptibility, the fluctuation of the parameter scales. And if it diverges, or becomes bigger and bigger as you increase the volume, that's a sign of a first order transition. Okay, so now going back, so we have the order parameter, we studied it, we determined the transition temperature. Now, yes, please. Why not use the Wilson loops? Because your time, the Wilson loops has an easy physical interpretation. It's zero temperature, right? It obeys the area law, and that means confinement. Now we are at finite temperature, and you cannot go to infinite time, right? So there is no area law per se because your time is limited. So you can only go up to the inverse temperature, and then of course it naturally gives you the Polyakov loop. And of course, that's one way to think about it, if you, why not Wilson loops. But the other thing is that, of course, is this transformation, right? So you think there is, I mean, if you ask, okay, so there is a confinement, and the area law is a signature of confinement. We're talking about deconfinement transition, right? So now we're talking about possible phase transition. There has to be an order parameter. And if there's an order parameter, you think should be a symmetry. Right, and what is the symmetry is, and I was arguing that the ZN symmetry, and the thing that transforms non-trivial and the ZN symmetry is a Polyakov loop. Yeah. Okay. So now we could also consider the correlation function, and that's actually, so that slide is important because it goes a little bit back to your question. I mean, there is no area law per se at finite temperature, but there is something similar, right? So you consider the Polyakov correlation function. So again, you put the Polyakov at point 0, point R, and kind of study them as function of distance R. And then you see that at temperature below the transition temperature, you have some sigma times R over T. So that's, if you wish, a generalized area law because now time is finite, but you still have this exponential behavior. So you could extract now the string tension at non-zero temperature as function of T. And here I show the numerical results and the fit to the numerical results of these dots. So you see that the string tension kind of decreases, the temperature decreases. So here I normalize the string tension by the zero temperature string tension, which again you could calculate as a lattice, and the temperature at 0.9, it's like 0.6 or 0. Maybe a little close to half of its value. And of course, you could also go to lower temperature and see that it goes all the way to the zero temperature. So at zero temp, as you go to lower and lower temperature, it approaches the zero temperature string tension, but then it decreases. And of course, if you would have a second order phase transition, right now, look at this expression, right? It basically tells you it's a correlation length, right? So the exponential decay of the correlation function of your order parameter is a spatial string tension. And if you have a second order transition, phase transition, the correlation length goes to infinity, meaning that sigma has to go to 0. That doesn't happen here because that's a SU3 gauge series. So here we know that transition is weakly first order. And therefore, the string tension goes to some small value, but non-zero value. Now, what happens when you broke the ZN symmetry, you go above the transition temperature? Of course, the polycube itself is non-zero, so that means that you have a disconnected contribution to the correlation function. So you, instead, what you have to do, you take the correlation function, you divide by this disconnected contribution, or you could subtract and divide, doesn't matter, but that's probably the simplest way to look at it. You take the logarithm, and the logarithm of this combination also should decay exponentially. But here it has a different meaning. It has a meaning of screening length or inverse screening length, or the screening mass. So you could calculate now the screening mass again on this lattice. So you do the calculation of that. You extract the screening mass by exponential fits, and here the screening mass for different n taus. So from 4 to 8. So you get a sense, of course, there's some discretization effects, not too large, being that this is an infrared quantity. And you see that the screening mass goes to is large. So the screening length is relatively small at high temperature, but then goes to zero, not quite to zero, but goes pretty close to zero, but it's very small at transition temperatures. So somehow the plasma gets unscreened at the transition temperature. Yes, question? Mm-hmm. It has, but that's kind of a story which I'm going to continue. If you go to shorter distances, then you could get, I mean, then of course it has a well-defined meaning and interesting physics by itself. I mean, here I just give you a general idea what it goes. There is you see screening from lattice calculation, and of course you also see that the screening vanishes as you go closer from the high temperature regime. And as a confinement, right, the string tension, the string disappears because the string tension goes to zero. Those two things. And the prefactor, of course, that's interesting. That's probably going to the next slides. Now you see that both the string tension goes to some very small values at the phase transition, the confinement phase transition temperature, and the screening mass also goes to value. And the small value means that the transition it's a first order transition, but very weakly first order phase transition because correlation length also doesn't go to infinity, but it's compared to your physical scale, the temperature is pretty small. Also, the scale is energy scale, the mass is pretty small, meaning the correlation length is very large, even though not infinity. Okay, good. So now let's go back to the normalization of the polar cube. So up to this point, we didn't care about renormalization because we only cared about either the polar cube at finite lattice spacing and its fluctuation, which has a well-defined peak that was good enough to locate the critical point or the pseudo-critical point, and also the correlation length. So those don't have to worry about overall renormalization, so don't have to worry about amplitude. But now, eventually, we want to worry about amplitude. Let's say, one way to say about, so how do we renormalize it? And the realization is that if you have a quark anti-quark, right, and you have a potential and you define your potential somehow on the lattice, it's arbitrary, but you could agree upon some definition of the potential at zero temperature. Could be a phonological potential to describe, let's say, bothonium spectra, as I will show in my next lecture, hopefully. Then it's fixed, right? And then you say that, well, the effect of the temperature at very short distances when a quark and anti-quark are very close to each other, they interact like they would interact in the vacuum. So your free energy should be the same as the potential at very short distances. So the distance is much smaller than inverse temperature up to some normalization factor, which is come from the how you normalize a trace. So there is T log 9. It just comes from the fact that when you look at the polar group correlation of the free energy of quark, you normalize by colors. When you talk about potential, you usually don't normalize by colors. So that's kind of a trivial normalization factor. So you assume, so basically you take your free energy, you normalize to the 0 temperature potential at very short distances by fixing kind of defining what the normalization of the potential is, and that gives you a renormalized free energy. Now, if you go to large distances, so once you fix this normalization, you just simply go to large distances of your polar correlation function. And of course, the fact that you have screening means that at very large distances, the free energy of a quark anti-quark is finite. And in fact, at infinite separation between quark and anti-quark, this finite, so that's F infinity, so that's free energy at infinite separation of quark and anti-quark is just twice the free energy of an isolated heavy quark. So basically, when you pull them apart to very large distances, you have just twice the free energy of a heavy quark. So this FQ or F infinity value 2. Now, if the polar group, right, is the free energy, then you just say, well, the renormalized polar group is a renormalized free energy of a quark anti-quark pair divided by 2, or not renormalized free energy of quarks, to the exponent, right? So that's basically would be your definition of the renormalized polar group. And now you could look at it as function of the temperature. So you do the renormalization, you take your lattice data, at each lattice space you renormalize it. And here I show the lattice results to different n tau. So remind you, n tau going to larger and larger values, so 4, 8 to 6, that meaning closer to continuum limit. And here's the results, right? And you see that all different lattice spacing, different symbols kind of are on top of each other. So meaning that instead of going to 0, now it goes to a well-defined value. And here you clearly see that below the transition temperature, you get 0. Then it jumps to some non-zero value like 0.4, 0.3 at the transition. So that was the scale I mentioned before. And then increases, and of course, asymptotically, it should go to 1, right? If the quark wouldn't interact at all with its surroundings, then this free energy is trivial, so you should get 1. Of course, you don't get 1, you get something which is interestingly enough larger. Now, how do you understand it? You could calculate the free energy of a static quark in perturbation theory. And the result is kind of amazingly simple. It's a 4/3, so it's just basically the CF, the color factor, fundamental Casimir, alpha S times the Debye mass, so the inverse of the Debye, so screening length. So basically what it tells you is that alpha S is clear, right? That's, or even this prefactor, CF alpha S, that's basically just a color charge of your quarks, how it interacts with the medium, and M Debye is just what is a scale where it kind of interacts with, right? Well, the inverse length scale, and that's M Debye. So when the coupling goes to 0, of course, the free energy goes to 0, but it does so kind of is a negative sign, so meaning that there is a negative free energy from this quark interacting with the medium, and therefore the polar group goes above. Now you could also calculate kind of the entropy of the static quark and so on, and that I will discuss maybe on the next slide. Okay, so that was pure group theory. And now we could go to full QCD, so physical QCD, 2+1 flavor, physical quark masses. That's how the calculation looks. That's much more modern or much more newer calculation. What I will show you, some of that was from the last century, 20th century, and the very end of the 20th century, beginning of 21st century. That's like only 8 years old or whatever. So that's a newer calculation. So here I show the free energy of a static quark, anti-quark in QCD with this trivial factor subtracted, compared with the 0 temperature potential, shown as this black line. So that's the 0 temperature result. And for some reason, the symbols here which show the temperature disappeared. Interesting. Anyway, so those are the temperature from very low to very high. What you see is that indeed there is a color screening sets in. So at very short distances, at least when the temperature is not too high and you could go to short enough distances, you see that the free energy agrees with a zero temperature potential, and then start to break off, and that is the screened. Of course, you have screening even at very low temperature, even below the deconfinement transition, because in principle, when you have dynamical quarks, you have something called string breaking. When you have enough energy in the string, then the string breaks and you no longer have this linear rise. So that's why the free energy, even at low temperatures, this blue line is kind of plateaus off. But then as you go to higher temperature, it's kind of breaks off from the zero temperature results and goes to a constant at shorter and shorter distances. And the gray line here is basically the perturbation theory result of the potential. So that's what we don't have lattice results. We use a vacuum perturbation theory to calculate the potential. And again, you see that very short distances, you always agree with the zero temperature potential. So we see that at large distances, the potential is screened, and this distance where the screening sets in becomes shorter and shorter as the temperature increases. But at short enough distances, you always recover the vacuum potential. Now, so we have calculated the free energy of quark antiquark, so we can calculate obviously renormalized Polyakov group. And here I show the kind of the summary calculation of the Polyakov groups in SU2 gauge theory, SU3 gauge theory, and QCD, full QCD with physical quark masses, so physical strange and physical up and down. This blue line, two lattice calculation using stout discretization and highly improved staggered quark discretization, his discretization. After taking the continuum limit, of course, they agree as they should. The interesting thing to note is that the behavior of the Polyakov group across the temperature is very different, right? So here we have 0, jumps to non-zero value. Here we have the SU2, eventually it goes to 0 around slightly above 300 MeV. So there is a second order transition, so the order parameter goes to 0 eventually. But the overall behavior is very different, right? So namely, when you look at the transition temperature, which I will show next slides, which happened around 155 MeV, the Polyakov group very small and very, very smoothly. So you don't see any kind of behavior, kind of marked behavior in the Polyakov group, let's say around 150 MeV. So where is the deconfinement transition?
This SU2 and SU3, why did they calculate temperatures below the deconfinement transition temperature?
Well, it's 0. I mean, if you take
it jumps and
yes. I mean, of course, if you have a finite box, it doesn't go to 0, right? Because the largest separation between quark and antiquark is your lattice or maximum lattice distance, right? So it's some very small number, but it's finite. But of course, if you take the thermodynamic limits, it goes to 0.
Some of the that should be more continuous.
Yeah, but the problem is that, of course, you have humongous finite volume effects, right? The correlation, the length diverges, so kind of getting that close is already challenging. And you could nowadays, you probably did. I mean, that's some, I collected some, again, some of my calculations, some from Bielefeld, or maybe the better one now. Yeah, but it's back then when we started doing this, calculation, it was difficult to get very close to TC, so that's somehow stopped there. Okay, so one thing is clear. So pure group theory is very different from QCD in terms of how the Polyakov group behaves, and the transition of the Polyakov group has a very smooth transition or very smooth behavior around what we think is a transition temperature in QCD, and then that of course raises the question: what is a Z3 symmetry if it plays any role in full QCD? Okay, so now you could look at this more differentially. So when you look at the Polyakov group, you see nothing, but of course, it's always a matter how close you look at it. So the best quantity somehow to look at it is actually turns out to be the entropy of static quark, not the free energy. And the reason is simple, or the polar group, right? The problem is that the free energy has this normalization, well, I would say arbitrariness, right? It's a constant shift, right? So you want some quantity which kind of independent of your convention of how you normalize your potential. And any constant shift in the free energy is kind of is gone when you take the temperature derivative. So that's only the genuine temperature effects mean. So it's not the value of the free energy per se of a static quark, which has a physical meaning, it's variation with the temperature, which has physical meaning. And of course, if you look at the polar group, it's even worse, right? Because now here you have to take this constant shift and it kind of enters in a non-trivial way in the exponent divided by the temperature. So you want something which is simple. The simplest possible way is look at the entropy of static quark, which is just a minus the derivative of the free energy by the temperature. And look at the cross deconfinement transition. Again, we did this calculation for different n taus. And here I show the quark entropy as function of the temperature for different n taus. And you see that the entropy develops a peak. So that's in full QCD. So it increases up to the transition temperatures and then decreases. And you could kind of play this game for, so that's basically the smallest lattice spacing, and you go to the finest lattice spacing you have. And now you could also compare it with the chiral transition temperature, which I will discuss next. And in the chiral transition temperature, you see that they're shown as this horizontal, this vertical band. And the position of the peak in the free energy for static, the entropy of static quark coincides with this band. So in that sense, the screening, or the deconfinement, which corresponds to the peak in the entropy of static quark coincides with the transition temperature in QCD, which is defined as chiral transition temperature. So in that sense, chiral transition temperature and deconfinement transition temperature agree. Yeah, so okay, I didn't discuss yet the HRG, but the black line within the figure is basically a hadron resonance gas calculation. And the hadron resonance gas calculation here is basically the gas of a static light hadron. So you have a static quark, it can couple to light quarks, so that's forming static light mesons. And you have an entire excitation tower of those. You could also couple to light quarks, two light quarks, so forming static light baryons, and that you could also kind of put the entire spectrum. It has been calculated on the lattice, at least for ground states. For the high excited states, you could infer from Quark model what the value is, and that's what goes in. And of course, the entropy of a static quark in this HRG also increases, but the pace of increase in real QCD is much bigger. So here, for describing deconfinement transition, of course, HRG completely fails. That is, no, it's we put it in everything that we could think of. I mean, the entire spectrum, not even the states that measured or calculated on the lattice, everything that you could take from Quark model. You could even put more, but it doesn't matter, right? Because eventually you put more and more, and it doesn't help you because it's exponentially suppressed, right? So you go to very high in the spectrum, it's still 160 MeV or whatever, so that's exponentially suppressed. So you can't possibly put enough states in the hadron conceivably that would compensate this shortfall. So just think what it says that this hadron gas, although it may work below 120, 140 MeV, as you go close to the chiral transition temperature, because that's now the chiral, the deconfinement is not very well defined, except for the peak. Or you could say, well, if you want to think about this peak as a deconfinement transition, then as you go closer to the deconfinement transition in QCD, this hadron resonance gas obviously breaks down. No, there's a demonstration of complete failure of hadronic decrease of freedom. There's a demonstration of deconfinement, I would say, because you will see that it actually works much better in other cases. But here we're looking at, it's like, think about it this way. if you calculate, let's say, pressure in hadron gas in the lattice, and I will show you they agree, or even if they disagree, they don't disagree by much, right? Because you have a crossover transition pressure. Even if you have a phase transition, doesn't matter. The pressure is continuous. And if you get it right at some point at low temperature, it won't be totally wrong even at high temperature. But if you talk about other parameter, which is sensitive to some sort of transition, because there is no way you could describe it in terms of low energy degrees of freedom. Yes, Jean-Paul.
The other physical piece, because the quark is fixed, right?
Yeah.
At a fixed position. So there is no entropy associated with.
No, that's the entropy of interaction. Yeah, but it interacts with the medium. It disturbs the medium around it.
Is it the screening cloud?
Yeah, the screening cloud, right? So, well, of course, I don't know. I mean, it wouldn't be, of course, I know that because it's calculated. So that's just reading out a perturbation series. So that's my interpretation, right? So there is a heavy quark. It interacts with alpha strength with the surrounding. And it's also somehow it's given by the divine. Yes. So it is what it is, but it's basically the Debye mass, right? So if it tells you if the Debye mass is small, then free energy is also small, and if the Debye mass is large, then somehow it. I mean, okay. I mean, if the Debye mass is large, it means that you have to have a lot of color degrees of freedom within the Debye sphere. That's right, and then of course it's proportional to the Debye mass because you have a lot of stuff in the Debye mass. Oh, okay, that's in the high temperature, right? So, and okay, so in the high temperature, we sort of understand it goes down, right? It goes down, and why it peaks? Okay, that I would think that somehow. So here, if you think of a hadron picture, right, you have possibilities to attach this heavy quark to another quark forming a light meson, a static light meson. You could excite the static light meson. It all ends up to this entropy, right? You could also end to baryons that adds more entropy. But somehow, as you increase, you go closer to the transition temperature. Somehow, all these normal states won't be enough, and you have to somehow attach to even more states which are not even there. So yeah, so in that sense, you mentioned hagedron. So if you imagine somehow the number of states exponentially increase, then of course that may be it. But simply that would be an increase in number of states that is not manifested in the QCD spectrum because QCD spectrum is not hagedron, right? Because if you go higher and higher, eventually you reach a hard scale and the spectrum has to go down. So somehow in the medium, maybe there are some more states when hadrons start to interact and they form some. So that's kind of a specific to find. I don't know, have a good understanding. So I understand it in hadron gas to a certain point, right? You could attach the static quark to more and more combination of light degrees of freedom, but that of course you below orders of magnitude because it's entropy, right? So you're missing orders of magnitude number of states. It's kind of a bizarre, but yeah, that's the best I could think. Yep.
Hello. When I see that in tau is around 6, so this temperatures is shifted, I mean, towards the increasing side, 160. For in tau is 6. The first
you should, right. That's right. The chiral transition, as you decrease the lattice spacing, becomes smaller.
Yes.
Right, and as just a lattice artifact, right? So you have to take the continuum limit. So I show it this way because the 6 is it's easy to calculate, right? But then you have to compare with the chiral transition at Z and tau at that lattice spacing.
I mean, what is the physical picture? So why it is?
Why it's there is no physics, there's just discretization effects, right? It's just discretization effect in that very specific discretization scheme that I'm using here. There is no, I mean, when you talk about discretization effects, there is no physical picture, right? It's depending on which one you choose, it could go from above to the continuum or from below.
The shifts is, I mean,
Yeah, no, the shift is significant.
significant.
I'm not saying that there is, yeah, so it's 165 and goes to 160, so it's 5 MeV shift by going from 6 to 8, from 6 to entire core 12. So that's of course, you have to always take the continuum limit. I mean, I could have showed you everything in the continuum limit, but then it would be messier. Maybe next time. Okay, but here's the continuum results too. So just continuing with the entropy of the static quark. So here I take as a continuum limit, and that's a blue line. So you see, once you take the continuum limit, it becomes messier because errors increase, but okay, you still can do the calculation. So this red band is the entropy of static quark in the continuum limit for the physical point. Now you could ask the question how it changes. Imagine you change the quark masses. You take the pure growth theory and F equals 0, meaning the quark mass is infinite. So those are blue points, and then the entropy goes up, and it basically diverges at TC, right? Now you go to 800 MeV pion mass, so you take some very heavy quark, where the pion has 800 MeV, have the red points. It also increases almost by the same amount as in pure growth theory. It goes to finite value and then decreases. You lower pion mass to 440 MeV, you have this blue, and the peak goes decrease. And then, of course, by the time you go to physical, not quite, but almost physical, 160 MeV, that's when you have this very washed out peak. So you clearly see that as you go from infinite quark mass to lower and lower quark masses, the deconfinement transition kind of gets washed away, and only some remnants of it remains as a physical point, or close to the physical point.
So the peak is always very much visible.
I mean, compared where it was, yes, it's still visible, but it's kind of significantly washed away. Yeah, so it's kind of the entropy. And now, if you think about this previous question, right? If you have a true deconfinement transition, right, everything is heavier, and the increase in terms of the spectrum of hadrons, of static white hadrons, yet the increase in entropy is much bigger than you had in the QCD. So somehow, when you go to heavy quark masses, heavier quark masses, not infinite, but heavier, 400 MeV pion, somehow this failure of hadron gas will be even more apparent, because hadron gas will go down and the entropy goes up. So somehow you're missing a lot of states. Okay, so that's at low temperature, but you also see that at high temperature, the entropy decreases. So you could ask the question, can I calculate this entropy? And I already showed the leading order result for the entropy. So that's here it is. So the lattice data is black points. The leading order result is this red band. And okay, the width of the band is a scale uncertainty. You have to vary the perturbative scale to some reasonable range that gives you the band. Then you go to next to leading order, then you have this band between these dashed lines. So again, the scale variation increased, but the result didn't change so much. And then you could go to next to leading order, and then you get this purple band. And okay, so here, I mean, you have a meaningful comparison in the sense that the width of the band is small, but okay, it only agrees with perturbation theory quantitative level only at very high temperature. But at least if you go to very high temperature, 2000 MeV, you could make contact with perturbation theory. Lattice agrees with perturbation theory. Yeah, there's a perturbative calculation, different orders. So the leading order is red.
What are you computing?
Like? The entropy of a static quark.
So you put like a heavy quark.
Heavy quark, and you calculate its entropy. No, you calculate free energy, and of course, then you take just derivative. Yeah, thermal QCD, that's all.
This uncertainty will be by.
Well, it's due to the coupling as the bymass. If you go to next to leading order, you have additional terms, but you don't have anything to compensate the scale dependent to the coupling. So that's why the uncertainty band increases. You go to next to leading orders, and you picking up the first correction, which compensates the scale uncertainty in the coupling constant. And the bymass scale uncertainty, that is still yet another order you have to go.
What is the parameter? Is alpha S?
Alpha S, and alpha S is some scale, so it's MS bar. Let's say the calculation on MS bar scale, so alpha S at some scale. So the scale from MS bar we take between 1 and 4 pi t, because pi t is a much broader frequency. Right, so that's a typical scale.
Next CD, what is alpha is?
It's alpha s cubed. So it's pretty high in terms of alpha s. Of course, one shouldn't be fooled by the high order because it starts with alpha s, just because the particle group expands and you have the biomass that gives you extra powers. So there are a lot of extra powers which are nothing to do with real order. So here, of course, next to leading order, the only beta 0, the leading beta function enters. So beta 1 you never even see in any serum.
But you've not taken a high temperature then?
No, that's high temperature in the sense that, of course, you assume that temperature is hard scale, and of course it is, because T itself is 3000 MeV, let's say, right? Then you have a factor of pi, because that's typically how the scale works out. It's not just the temperature, it's pi times T. So yeah, pretty much it's your mu scale is high.
That means some HTL.
Oh, HDL, of course, it's included. It's actually, I didn't mention, but that calculation was done in EQCD framework. Yes, sorry. Well, I would say, I don't like to, yeah, I mean, in formal it's in G, but I don't like to think about it's a G. Yeah, absolutely. So yeah, no, the physics of the bar screen is explicitly in there, yes. So yes, so I like to think as double expansion is alpha s and md over t, right? So when you do any calculation of thermodynamic quantities, there is always a double expansion. And then you see it's an effective field theory, right? Because if you do EQCD, of course, you have the hard contribution. It's a strict alpha s expansion. You have the soft contribution where the expansion parameter is typically gt squared, g squared t, so, or if you want the coupling of EQCD, E squared over 4 pi md. That's your expansion parameter. And of course, formally, this expansion parameter is for the g, so it's not g squared. So you have the alpha s in the hard sector, but in the soft sector, the expansion parameter is g. However, g is not a small number, right? So then the expansion wouldn't make sense, except that the real expansion parameter for thermodynamic quantity is not g itself, it's always ge squared over 4 pi md. And that happens to be small. And actually, when you make the Debye mass large, right, the g is meaning that g factors are larger, but this expansion parameter actually becomes smaller. So going to the low temperature limit, it's not a problematic expansion. The only problematic thing is a matching between the hard sector and soft sector, because it goes through the logarithm, and of course you don't have that many walks, right? So I would say, conjecture that if you would be able to go to higher order, actually you would see that it kind of gets better. And just keep in mind, right? It doesn't look good, right? It's 3000 MeV when you make contact with lattice, but here you only have beta 0. Right, and it's formally it's higher than alpha s, yes, but practically it's maybe 1 loop, 2 loop. Okay, good. How much time do I have? 20 more minutes? 10 minutes. Okay, so okay. I'm going much slower than I anticipated, but good. Hopefully, people get more out of it. I covered a lot. Okay, so now let's go back to perturbation series. So now for the particle correlator and calculate the free energy, right? So the particle correlator gives the free energy of the static quark anti-quark pair, and we could calculate it in perturbation series if the temperature is high. And okay, why we're interested in quark anti-quark pair free energies is because basically that gives you a work that is needed to separate a quark anti-quark from distance r1 to r2, more precise, the difference in the free energy at R2 and R1, that's the work we have to do to separate quark anti-quark pair. We can calculate this object in leading order of perturbation, so you can have this expression, so it's Debye screen, so you have 2md over R, but the prefactor is interesting, right? So it's alpha s squared over r squared t. Now, if you do a similar calculation, let's say, or in QED, when you have like electric charges, static electric charges, or very heavy, you try to do the same thought experiment of separating them. The corresponding free energy will be just a screened Coulomb potential. So this is Yukawa type potential. With again, the Debye mass, which is almost the same as QCD modular prefactors, right, and C and so on. So it's here we understand what's going on. The interaction is screened and the free energy is therefore smaller. But here we're changing completely, right? We go from 1 over R to 1 over R squared. So why is that? And of course, you at infinity, you have this by the static charge, the free energy start the static charge is additive constant. Well, the conjecture is that in QCD, this work is reduced because now you have two color orientation of a quark and anti-quark. You have the singlet, right? Like that's what you have in QCD, right? You have electron and positron. Here you have quark and anti-quark. Is forming a color singlet, but you have other possibilities that the quark and anti-quark is an octet. And the octet is also a Coulomb potential, strictly speaking, but a repulsive one, right? So when you do this work of separating quark and anti-quark pair in a QCD medium, the medium can flip the color of the quarks, right? The interaction of this pair, and it becomes octet, and the octet, when it's octet, it repels. So effectively the work that you have to do the separation of a quark and anti-quark is less, and that's why it decreases like 1 over R squared. And of course, it's also now twice the Debye mass instead of the Debye mass because now it just how it adds up. And then of course, now if you, so that's basically when you do a straight perturbative calculation, but you could kind of reorganize your calculation a little bit. So you, for example, you use a Fields identity. You could write your Polyakov correlation function as a decomposition of color singlet and color octet contribution. So we have this weights 1 over 9, that's for singlet, and 8 over 9, and that's understood because you have 8 gluon, and the total combination is 9. So that's why you have 1 over 9, but it comes out of the color algebra. And here, of course, when you do this Fields identity, there is another type of correlation function appears where you trace the Wilson line. So now we just have if L is a trace Wilson line, here untraced Wilson line W, and that's what defines you as singlet free energy. And of course, to define it, you need a Coulomb gauge. Well, you could do other gauges, but a physical gauge, a natural choice would be a Coulomb gauge. You can do the calculation at leading order and perturbation. So you could calculate this object. You could calculate the corresponding octet contribution. And then you see what I already said, that in the singlet channel, you have an attractive force between quarks. It's just like in QED. It's just modification of the color charge. And in the octet channel, you have a positive force with a corresponding color factor. And now if you insert these two expressions, so here you have like 1 gluon exchange into 2, and you insert back, then of course you have a cancellation of the leading order result. So your free energy of a quark anti-quark pair actually is given by 2 gluon exchange, not by 1. But and basically with this simple kind of trick, you can kind of understand why you get this result. So we have this interplay between color singlet and color octet channels. But yes.
Almost like a dipole. Dipole.
Yes, that's where I'm coming at. And now, of course, okay, so that's a conjecture how it works in lattice QCD. So, of course, on lattice, you could also fix a Coulomb gauge. You can calculate the singlet free energy. You could calculate the physical free energy. And here I show the calculation. The dashed line is a 0 temperature potential. You have calculated the singlet free energy. You see nicely that it agrees. At short distances, you have a screening, as you would expect. You have the same picture for the free energy, except now you see the temperature dependence of the free energy is much bigger than the singlet free energy. And that's because, and of course, again, at very short distances, it still agrees with 0 temperature potential, but it breaks away from the 0 temperature result at much shorter distances. And that's, of course, this difference between the singlet free energy and the free energy is just because you have the octet contribution. Now you could try to do the same trick. You could calculate the singlet. You could assume that the octet is just 8 times the singlet and try to reconstruct the free energy of a quark. And then that is shown here in this figure with a subtraction. So the free energy goes to 0 instead of a constant value. And the open symbol as a reconstruction using this simple-minded form. and the field symbols are the actual lattice calculation of the free energy. And you see that, okay, at lowest temperature, maybe it doesn't work so well, but as you go to higher temperatures, this picture of free energy being emerging from color singlet and color octet channel getting better and better. Now, the question is, okay, so that kind of works, but it requires us to fix the Coulomb gauge to define the singlet free energy. So is it possible to have a gauge invariant decomposition in some sense of the free energy into singlet and octet contribution, because that's kind of the physics intuition. That's why it behaves the way it behaves. And here the answer is yes, and you could do it. And for that, you have to use an effective theory approach called potential QCD. I will explain maybe in my next lecture what it is. But when you do it, you could, of course, you could do it in the realm of validity of QCD. So this effective theory is valid for distances much smaller than the inverse temperature, at least the formulations that we needed. And in this regime, you could write the free energy as a correlation function of singlet quark fields and the octet quark fields times the adjoint Polyakov loop here. And then, of course, each of these correlation function defines you have singlet and octet free energy, and these are gauge invariant by definition, because also, I mean, here it's gauge invariant because it's a singlet field, and here it's of course you have the adjoint, which ensures gauge invariance. So you could calculate in QCD in perturbation theory in this limit of small r. You recover the vacuum potential, Vs, the singlet potential. You recover the vacuum octet potential as some thermal correction, which you could in principle calculate. And you could also calculate the entire correlation function, entire contribution. And you see that the naive Coulomb gauge definition, Fs and Fo, actually coincide with QCD definitions or results up to this correction. So when you go to very small distance limit, you could, in principle, do this decomposition and kind of engage in invariant manner and actually calculate systematically the thermal corrections. Now, what happens if you go to large distance regime? And of course, here you also can use effective theory.
If you're doing it in some large QCD,
yes.
What is this N suppressed?
The octet is unsuppressed, yes. So in the large QCD, you have only the octet potential itself is 1 over NC. But it's NC squared, right? Because in the singlet is NC squared minus 1 over 2 NC. That means the singlet is proportional to NC, octet proportional to 1 over NC. Right, so it's basically NC squared suppression, because the relative suppression is 1 over NC squared. Okay, so if you go to large distances, of course, let's say of orders of the biomass, you have to use another effective field theory called QCD, which I will show in the next, I have 5 more minutes. Okay, so let me just show this, how this QCD calculation compares with the lattice results. So here I show the difference between the singlet potential, or the potential, in that case is vacuum potential, and the singlet free energy calculated on the lattice in this Coulomb gauge. And of course, the QCD prediction, this difference should be very small at short distances, and indeed at short distances at RT for the 0.2 is compatible with 0. That's prediction is checks. Now, there is also a prediction for the octet, right? You have this decomposition to singlet and octet. To the leading order, the octet free energy is just the Casimir scaling of the singlet. So there's just a Casimir factor, 1 over 8 in QCD. Of course, if you go to high enough order alpha S cubed, there is correction to this Casimir scaling. So now if you know the singlet one, and let's say you calculate it from lattice QCD in Coulomb gauge, short distances doesn't matter. You do the Casimir scaling, then you obtain this green line. So just basically assuming the Casimir scaling, you obtain this green data points, the green line. The data for this combination of the free energy times the temperature times R squared, so we just get rid of this 2R squared to make it kind of nicely visible as a plot. That's the lattice results. The Casimir scaling and the decomposition gives you this green band. And if you add the correction to the octet, to the breaking of Casimir scaling, you get the blue band, you get much closer to the data. So basically what you see, the distances R times T over 0.3. The entire temperature dependence of the free energy is just given by this decomposition into singlet and octet. So here you don't see a color screening in the free energy at this small distances. What you see rather color deconfinement. So instead of only having single degrees of freedom, you also have the octet degrees of freedom showing up in non-perturbative calculation. And at these distances, you could actually quantitatively understand the lattice calculation if you use this framework and QCD. You could finally go to large temperatures and see the screening. So now you're looking at very large, or relatively large separation between quark and anti-quark. And you could, again, use perturbation theory. Then, of course, in perturbation theory, this prefactor, 2MD. And here I show the lattice results at 2 different temperatures and the perturbative calculation. And okay, there is not great agreement with perturbation theory, but somehow when you add the next 2 leading order corrections, encoded in this one, so the leading order result is this one, you can then add the next leading order correction. Actually, it goes to the right direction. You get closer to the lattice data. You could do the same trick for the singlet free energy. And again, at large distances, you see screening and quantitative with a prefactor we were talking about. Right? This is basically all that one that seems to agree more or less with the lattice results. So at distances, let's say 0.6 in R over T, you see the kind of the screening in the heavy quark anti-quark potential. Probably is a good point to stop. So I will continue next with the chiral transition finally. Okay, very good. Thank you very much.